You know, every single time you refresh your social feed, or you book a ride, or even just check your bank balance, you're talking to this global machine of just staggering complexity. But to you, it feels simple, right? It just works. Well, today, we're going to go under the hood. We're going to explore that unseen engine that powers our entire digital world. So let's pop the hood and really see how this thing works. Alan Kay, who was a true pioneer of computing, he just nailed it with this quote. The internet really does feel like a force of nature, doesn't it? It's just always there, always on, always reliable. But it's not. It's a man-made system. And making it feel that effortless is, without a doubt, one of the greatest engineering feats in human history. So how do they pull it off? What are the core ideas that keep this digital ocean from, just boiling over? Well, it turns out that pretty much every application you use, whether it's a huge social network or a global banking system, is in a constant fight against three fundamental problems. And solving these, well, that's the whole game. And here they are, the three big pillars: reliability, scalability, and maintainability. Okay, let's break it down. Think of it like this. Reliability. That's your car starting every single morning, no questions asked. Scalability? Imagine you own a small restaurant and suddenly a giant tour bus pulls up. Can you serve all those people without the kitchen catching on fire? That's scalability. And maintainability? That's making sure the car's engine isn't some tangled, chaotic mess so that years from now, new mechanics can come in, understand it, and keep it running smoothly. And here's the catch. You can't just be good at one or two. A system isn't truly successful unless it masters all three. Let's zoom in on scalability for a minute, because this is where things get really, really interesting. See, scalability isn't just a simple yes or no question. It's not a switch you just flip. It's all about how gracefully a system handles growth. The real question isn't, is it scalable, but rather, how does it scale, and what are the trade-offs we have to make to get there? Okay, to make this feel a little more real, let's just look at Twitter. On an average day, users are posting something like 4,600 tweets every single second. Now that is a lot, for sure, but here's the kicker. Handling that number of writes, new tweets being created, that's actually the easier part of the problem. The real monster is on the other side of the equation. Get this. For every one of those tweets being written, there could be thousands or even millions of followers who need to see it pop up in their timeline. So, Twitter has to serve about 300,000 timeline reads per second. That massive difference, that amplification, has a name. It's called fanout, and it is a huge scalability problem. One person does one small thing, and it triggers thousands of other operations. So, how on earth do you even begin to build a system that can handle that kind of ridiculous load?
Well, I can tell you the first answer is pretty simple. You absolutely do not do it with just one computer. At this kind of scale, even the world's most powerful supercomputer would just melt. You have to think bigger.
So, the solution is to distribute everything. The data, the work, the load, you spread it all across a massive fleet of thousands of computers. This is the absolute bedrock of basically all modern applications. But, and this is a huge but, as soon as you do this, you've traded one giant problem for 1,000 smaller, much, much trickier ones. Like, how do you keep all of those machines in sync? How do they all know what's going on? Okay, to solve this puzzle, engineers basically rely on two fundamental strategies. First up, you've got replication. The easiest way to think about this is like making photocopies of a super important document. You keep identical copies on a bunch of different machines, so if one of them suddenly dies, the data isn't lost. This gives you that first pillar we talked about, reliability. Then you have partitioning, which is sometimes called sharding. This is more like splitting a giant phone book into separate volumes. A through F go on this machine, G through M go on that one over there, and so on. This is how you handle massive amounts of data and spread out the workload. This gives you scalability. And even inside a strategy like replication, you have more choices. For example, in a leader-based system, one machine is the leader. It's the boss. It takes all the new information, all the writes, and the others are just followers that copy it. It's simple, clean. But if that leader goes down, things can get a little hairy until a new one is picked. Then you've got multi-leader systems, where several machines can accept writes. This is way more resilient, but oh boy, does it create a new nightmare. What happens if two people try to change the exact same piece of data on two different leaders at the exact same time?
And that very question, it leads us right to the absolute heart of the challenge. This is what many engineers would call the single hardest problem in building these massive, distributed systems.
This is the classic example, right?
Imagine two people on opposite sides of the planet both click buy on the very last seat on a flight. The airline system is spread across data centers in, say, Europe and North America. The signals are literally flying across oceans. Who wins? And maybe even more importantly, how does the system guarantee that it doesn't accidentally sell the same seat to two different people?
For these computers, trying to solve that problem is kind of like a group of friends trying to agree on where to go for dinner. But there's a catch. They can only communicate by passing notes to each other. And those notes might get lost, they might be super delayed, or they might even arrive in a totally different order than they were sent. How could that group of friends ever confidently reach a decision they all agree on? It would be chaos.
Well, this problem actually has a name. It's called consensus. It's the process of getting a whole group of distributed computers to agree on one single value. It is one of the most fundamental and one of the most difficult challenges in all of computer science. And it's absolutely essential for things we take for granted every day, like making sure a username isn't taken or, making sure that last airplane seat is only sold once. Getting consensus right is just incredibly hard.
In fact, getting it right can be provably impossible under certain conditions. There's this famous idea called the CAP theorem, and it basically says that when part of your network fails, when some of your computers can't talk to the others, you are forced to make a brutal choice. You can have consistency, which means everyone sees the same, correct, up to the second data, but some users might get an error message if they can't reach the source of truth. Or you can have availability, which means everyone always gets a response, but some people might be looking at slightly old, out-of-date information. The theorem says, in that moment of network failure, you cannot have both. There's no perfect system. There are only very, very difficult trade-offs.
So, with all of these crazy challenges, how does data actually get processed in the real world? Well, the answer is to start thinking of these systems less like a static database and more like a constantly running 24/7 data factory.
And inside this factory, there are really two main assembly lines. First, there's batch processing. This is like a giant, heavy-duty production run that happens overnight. You take a massive chunk of data, say all of yesterday's sales data from every store, you run a huge computation on it, and you spit out a final report in the morning. Then there's stream processing. This is more like a 24/7, always-on assembly line. It handles events one by one, as they arrive, in near real time. It never stops.
A classic model for that batch processing factory is something called MapReduce. So imagine your job is to count every single word in an entire library of books. It would take forever, right? But with MapReduce, the map step is like having thousands of workers each take one book and just list out every word they find. The shuffle step is the magic. The system gathers all those millions of lists from across the network and groups all the identical words together. And finally, the reduce step has workers take each group, like all the instances of the word the, and just count them up to get the final total. It's an incredibly powerful way to break a huge job down into parallel chunks.
And all of this brings us to what's really the biggest modern insight in this whole field. We're moving away from the idea of having one single giant database that tries to do everything perfectly. The future is what people call an unbundled database. It's this idea where you combine a bunch of powerful, specialized tools, one that's great for durable storage, another that's amazing for search, a third that's built for stream processing, and you just wire them together to build what you need. And this actually brings us right back to that third pillar, maintainability. Because using these clean, specialized components makes the whole system so much easier for engineers to understand, to debug, and to improve over time.
And that really leaves us with a final thought to chew on. The entire goal of this unbelievably complex field, from replication and partitioning all the way to the insane fight for consensus, it's all about creating better building blocks. It's about taking these messy, incredibly difficult problems and hiding them inside reliable tools. So the real question for the future is this: what amazing things could you or I or anyone build if creating an application that could reliably reach everyone on the planet was as simple and as fun as snapping together a few Lego bricks?